Hello everybody. Today we will look into what is the best angle, what is the best way to throw an object. Now assuming of course no air friction or other factors that are unforeseen in the physics problems, the basic physics problems, right? What is the best way to throw, let's say shooting a basketball, to get the longest distance possible? The same energy put in, right? The same strength that a person has, and still getting the best optimal distance. So let's do this. Let's draw a vector, right? Something we're gonna, let's say here is a right here. We're gonna start here, and we're gonna draw a vector. We're gonna have some distance, some angle, and some vector basically at which we're throwing an object. Okay. Now, let's say this is gonna be our velocity vector. Okay, v. Let's do this, v. And let me get a little neater here. Okay, and we have, of course, right, we have the horizontal component. Let's say this is our ground actually that we're throwing from and to. It's going to fall back on there. So this is our let's say our kind of the ground, right? And again, we throw an object, let's say from the bottom, from the ground, like a cannon or somebody short, jokingly so. And let's say we throw it at an angle theta. Okay, and also of course, we get the what? The horizontal and vertical components. So we can get the horizontal one right there. This right here would then be what? From here to there. Okay. This would be our Vx, right? The horizontal component of the velocity vector. Okay. So the horizontal, again, the motion will be determined basically by the Vx, and this vertical motion here, let's do that, will be determined by the Vy, and we'll look into how to find those components. So the idea being that you throw this object along this, right, in a vector, and so what's going to happen? Of course, the gravity is going to take it down, so eventually it goes up, 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 and then will fall. So let's see how that will look. Let's say it does this motion here. Let's do the motion another color. Let's say red. Okay, so let's do kind of thick color here. Okay, watch this. So we go, like, let's start here, and we go, 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 and eventually it reaches a maximum, right, where it stops going up anymore at this point, and it starts going down, right, and it's symmetric. It's the parabolic down parabola. If you look into, and we'll kind of look at that, the physics, right, if the velocity is based on the kind of the negative gravity times the time, right, then what happens is if you integrate, you get that the displacement vertical is based on a negative 1/2 gt squared. Basically, it's one of those one of the factors that determine our vertical displacement. And so you see that t squared is what gives us the parabola, right? So that's it. Let's say we end up right over here, and this is our distance, this long from there to there, right here basically. And let's just say that right there. That's our distance. All right. Just put a D right there. So the question is, let's find a formula for the distance. How do we do that? Well, let's find, first of all, let me kind of show you something interesting, which is, let me just draw a triangle this time. A right triangle, okay? Any right triangle. And let's say you do have a velocity vector, or any basically number, any length, but of the hypotenuse. But let's just say it's a v. Let's not talk about not the vector. Just what's the distance between these 2 points? The hypotenuse length is a v. What is vx and what is vy? Right, sub y based on the theta. Is there a way to find it? And this is basically polar coordinate conversion. That's one way to think of it. But I want to mention it this way. Okay, my students in trigonometry class usually get a better feel for this than students in the physics class. It takes a little math, just a very basic touch upon it. What in the world is a sine of theta? What is the definition of sine? Well, that's opposite, right? The idea being the opposite in a right triangle, the opposite side over the hypotenuse. Okay? And what does that mean? Well, let's look at our opposite. Our opposite's Vy, and our hypotenuse is just a V. Solve for the Vy, multiply both sides by a V, and you get V sine theta is the Vy, right? There we go. That's how you get the decomposition, basically the vertical component of the velocity vector at angle theta. Similarly, cosine theta, what is the definition of cosine? Well, that's adjacent, right, over what? Over hypotenuse still. And so that means that we're going to get the Vx, right? Let's say adjacent to this theta is the Vx now, over the hypotenuse V. And so when we solve for Vx, what do we get? V cosine theta, right? So you just bring this V over here, and you get Vx equals V cosine theta. Multiply both left and right sides by V, basically. Again, V is not 0. Okay, so now let's look at this. What are our equations in general for, in mathematical terms? Let's look at this for the physics kind of idea. Well, so look, if you talk about velocity, right? The idea being that velocity acceleration is, if you have a constant acceleration, it's basically the dv dt. So the velocity, now we're talking about just the numbers. So scalar basically is going to be, but it can be negative or positive. In other words, the direction is incorporated in this. But v is equal to initial velocity, and then how much it changes over time. If every time it changes by a basically the slope of it being the acceleration. So plus a t, right? That's the idea of how you find v of t or v, right? And then what about the displacement? It's really integration of this. Keep it constant, right? That would be the initial kind of x naught, and then plus what's the integral of v naught? It's v naught t, with respect to t, of course. And integral of t is 1/2 t squared, so 1/2 a t squared. That's where these formulas come from, one way to think about it, okay? Now our a here is going to be negative g, right? Which is approximately 9.81, depending on where you actually are in the world, okay? There's also 9.80 sometimes, approximation. Meters per second squared, all right? And time, well, how do we find time of this, this process of it flying around and so on and so forth? So look at this. Here's what I'm going to do. I'm going to say, okay, so our velocity, Vy, we know that, right? And the initial Vy naught, right, was actually equal to V naught sine t, right? That's the initial. Okay, obviously it changes. So Vy of t, let's just put a t there so it's not the same confusing as Vy above. Vy of t, the function, would be V naught sine t, right? Minus g of t, because it's a negative, plus a negative g, right, of t. A is a negative g. Okay, and then V sub x of t, well, that's constant, okay? There's no acceleration horizontally, unless we add a factor of friction or whatnot, which we assume there's not. So it's just V naught cosine t, and that's it, okay? Now, the distance, well, the distance will be, look, it's just going to be the horizontal, right? It's like basically distance sub x, okay? That's what we're talking about. And that's going to equal to, okay, what is it going to equal to? The initial distance, well, we start at 0, basically. And then we add the velocity, so we do V naught, Vx, right, times time, horizontal, okay? And then there's no acceleration also. So basically it's going to be, and the time, let's say, is a big T, right? Everything that happens, the whole long process. Time for entire trajectory, basically. Trajectory. Okay, so let's see. So that's going to equal to, we don't know that time yet. Okay, Vx, V naught, I mean, right? Let's substitute for Vx. Cosine t, cosine, I mean, not, well, cosine theta, excuse me here. So, of course, of the angle theta, right? So, it's a good thing we're doing here. This thing, so we're talking about an angle theta, sine of an angle, cosine of an angle, cosine of an angle, okay? And times the t, okay? So let's do this. Now, how do we find the time? It's a little tricky. Basically, what happens right here, this is symmetric, right? There's no reason it shouldn't be. It's a little parabola going down. And what happens at this maximum spot? Okay? What happens at the maximum spot? And you can actually look a little bit more into the detail of why this and that will be symmetric, why they're exactly the same shapes. Again, it's because it's going up, 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 up against the same gravity, and then when it's at 0, it goes down, 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 down. Now this velocity, v right here, will be the same v this way. Okay? Same. It's just kind of, the flip of the vy, but the vx will be the same if you look into that also. So look, anyway, at time, this is going to be time t right here. What's going to be time up there? Time here equals t over 2, right? Half of the trajectory traveled, especially in that symmetrical way. And then, of course, time here will be the t, okay? Will be the kind of the whole trajectory's time over 2. So that's a trick that we're going to do. And guess what happens up there to the Vy? What's happening to the vertical speed? Well, it goes from the Vy sine theta to basically 0, right? It stops going up. That's exactly that point where it's 0 there. And so what happens is this. Look, we actually have to do the following. We have to say, yeah, Vy of our t over 2, that time there, is equal to 0, right? That's a big trick. Put a star by it. And that's, of course, what's Vy. Remember, it's going to be V naught sine of theta minus a g of, now put the time, t over 2. Okay, let's do this. Let's solve for t over 2. We can do that, right? And so solving, let's see, we get that t is equal to, let's do this. Let's bring to that side gt over 2. So eventually t is going to be v naught sine theta, right? And then divided by g and times 2, right? Kind of flip the 2 and the g. And so anyway, we get this. Okay, now we know the time. What is, remember, our d? Let's go back to the d. D is equal to, we put the whole time in there, right? We already have the formula right here, that it's v naught cosine theta t, right there, right? So let's do that. Let's put this t that we know now in, because we know v naught sine of theta, the g, right? So it's v naught, okay? And then what do we have? Cosine of theta. And then t would be, let's put it in here, 2 v naught sine theta over g, okay? Now let's rearrange this just a little bit, and we get, let's get kind of the v naught squared out. And so let me do this. Let me actually do this as following: v naught squared over g, right? And then let's do the 2. There's a reason I'm doing this. 2 cosine theta sine theta together, right? And if anybody knows what you're seeing right here, it's a big trigonometric identity there, and you can do that from the sum of angles formula, and you can actually prove that easily with kind of I usually do that, the sum of angles formula from the triangle, divide two triangles, and alpha and beta, and the area of the whole triangle, basically there's 1/2 sine alpha plus beta. It's going to equal to 1/2 of sine alpha, and then, cosine beta plus a 1/2 sine beta cosine alpha, where you kind of do that rearrangement. So anyway, eventually you get that this is equal to, guess what? V naught squared over g, and then this is going to be, and this is kind of important, I have to show that, like I said, sine of 2 theta, theta plus theta. Okay, well, and so what? Okay, that's our distance. It's a formula. We know it kind of if we know theta. V naught squared, if you think about it, that's the energy, basically proportional to the energy you're putting in, remember? Because what happens is energy is basically like mv squared, or, for the kinetic energy, right? So, proportional to v squared is energy. So, you put in this energy, and have the kind of, that's what you had, and you can throw the ball always at this kind of, if you have how strong you are, based on, depends really kind of on, that gives you that. And so look, the idea is, how do we optimize? How do we maximize? So the maximum is, what is the maximum of theta? Maximum possible of sine 2 theta, okay? Because we're going to have this as constant. We're only going to be able to maybe change theta, at least kind of mess around with it a little bit now, and that's going to equal to 1. Right? When basically 2 theta is, what is that? Let's do degrees. 90 degrees. Right? Sine of 90 is the maximum sine gets in the 0 to 360, the 360 degree range. And so what happens when you solve, you get theta is equal to 45 degrees. And what I'm going with it, where I'm going with this is basically throwing an object at a 45 degree angle will give you the optimal distance, the maximum distance, given the energy you're putting in is constant. And of course, a little deviation with more friction, whatnot, you may lower the angle a little bit to increase the distance if you're actually playing basketball. And there's a lot of friction actually going on, so maybe like a 40 degree angle or something even less. So again, that just depends on where you are, what climate, what pressure, etc. But 45 degrees is the optimal angle for getting the maximum distance in the trajectory, throwing it at a speed, or at speed of v naught, and a vector v naught at an angle theta. All right, so that was hopefully a fun problem to look into, and have a great remainder of the day. And again, the summary was that the theta equals 45 degrees, right? Would give you the maximum distance traveled.